Much of our work in analytic engineering can be challenging. Diving into a sea of unstructured data, sometimes with a map, sometimes not, often without a clear direction. We must bring clarity and consistency to the chaos. In my brief talk, I hope to provide you with a few tips and tricks and practices on data modeling that I've learned along the way. My name is Alex Ryan, and I'm a data scientist at TIER Mobility in Berlin, Germany. I got into data in a similar way to many of you listening. I was interested in predicting things and found myself naturally building data sets, wrangling large amounts of data, sometimes scraped from Wikipedia and other public sources. I spent some time studying statistics and then found myself in Berlin, cutting my teeth on SQL, dbt, and the initial steps of learning the skills for data modeling. This year in June, I joined TIER, and it's been a blast working with such a large group of talented data experts. One preface before I begin. These are just my thoughts that I've picked up on my journey through the analytics ecosystem. I found these tips are what have worked for me and in team dynamics and allow us to build scalable and maintainable data warehouse and transformation pipelines. I do not consider myself an expert in dbt, but I'm still interested to share my knowledge I've learned these past years, mostly to assist aspiring analytic engineers on what areas to focus on when it comes to data modeling. If you think there is a better approach to the topics I discuss, please let me know or ask a question, because as many of you may already know, analytic engineering can be more art than science, and there is usually more than one way to solve a particular problem. So I'll be going through these generalized topics and what we talk about when we talk about data modeling. I will begin by clarifying what data modeling is in the context of analytic engineering and dbt. Data modeling has multiple meanings when it comes to the different areas in the data field. Data scientists and machine learning engineers may refer to data modeling phenomena statistically using transformational steps such as linear logistic regression, k-means clustering, or principal component analysis. When I speak about data modeling in this talk, I will be referring to the transformation steps that take place after one has extracted and loaded the raw data into the data warehouse. For example, ELT rather than the old standard of ETL. These transformation steps take raw tables or events, distill them into standardized tables that can be more easily managed by end users, be they other analytic engineers, data analysts, machine learning engineers, business analysts, or other non-technical stakeholders, and for loading into tools such as Looker or Power BI. We are building models, a condensed, distilled essence of the data that can be better used to derive insights. I'll just give a quick overview of our ELT stack at TIER. So with source, in terms of sources, we obtain data from our own internal microservices from the product side of the company, as well as external third-party tools such as Segment and Freshdesk. At the moment, we currently extract this data from S3 buckets, although there are plans to move to Kafka, where we'll be ingesting the events ourselves. From the S3 buckets, we use a platform called ETL to load the data into a staging table on our data warehouse on Snowflake. This step involves flattening the raw JSON files in the S3 buckets and performing minor changes such as typecasting, formatting, and general standardization. From this point in the transformation stage, magic of dbt begins. From raw tables, we build a network of models with the end goal of providing working tables that can be used to easily derived actionable insights. Sticking to a consistent segregation of models is ideal because it allows analytic engineers to compartmentalize the different models into different categories and provides a framework for adding new models. The master schema or core models are where we expose these tables to Looker or for use by our data scientists. Many of our core models exist as fact and dimension tables. These exist as the building blocks for developing the aggregated data marts that incorporate business logic. DIM tables should contain an exhaustive list of the components, such as a list of all customers, suppliers, or vehicles. While on the other hand, a fact table should contain the repeated events, such as a list of orders, rentals, or page views. And a good analogy I've read is that fact tables contain verbs. And another analogy is a fact table tells a story, whilst a DIM table is the table of contents. I mentioned data marts. Like I said, these are tables that contain aggregated data, sometimes incorporating business logic, and usually involve major, computationally expensive transformations. These might include a sessions table that aims to list out the records that detail each user session on a web page or app. One particular data mart at TIER is modeling scooter idle time, which I can say from personal experience is quite a complex undertaking. From models, we move to CTEs or common table expressions. These are the modular select statements, can be chained together, each CTE representing a transformation that builds towards the end result of the model. I see them as micro models inside the larger macro model. Each CTE should do one core thing. That may be a similar transformation step that is applied to a handful of fields, something that filters out select rows, or adds a field that is utilized in later CTEs. Each CTE should have an alias or label that describes the said function being performed on the data. For example, you may have a CTE step that removes duplicate records, and so the natural CTE name might be remove duplicates. After you have established the core fields being pulled from each prerequisite model, it shouldn't be necessary to write out each column again. Instead, use a star where possible. I usually have the star at the bottom after I've created the new fields within the CTE. This is so that the newly created fields will appear first when testing, and I will not have to scroll to the very far right to see the resulting change. Others prefer the opposite, so the new fields appear at the very end, but to each their own. So this might be considered a controversial opinion, but I do not like nested queries in models. A nested query is shown in the image in the top of the slide, where it contains another select statement. Nested queries can sometimes produce elegant solutions, but in a team setting, when there are multiple analytic engineers maintaining a data warehouse full of models, nested queries are not really ideal. When our books and sentences flow in one direction, at least for English, I believe our data model should also have a flow in logic in one direction. This structure also makes it easier to access the function of each CTE, its resulting output, and how each CTE chains together to produce the end result of the model. I like to write each new CTE with the comma, the alias, or the label, and the bracket all on the same line as shown in the bottom example. When building, testing, or debugging a model, one can easily comment out this line, select only the code from the last line of this CTE until the top, and run the code, and you will obtain the result up to that particular CTE. This is really helpful. It's proved helpful for me when testing my models in the initial stages of development. And lastly, the final line, select star from final or select star from processing, allows you to easily swap this in for another CTE in your model. When you run the model, that is dbt run, you will now see the result of this particular CTE. Having a family of models with the same upstream dependencies means that there should be more consistency with results, less overhead maintenance, because each model works in modular form with one another. For example, a change in one upstream model will flow into the downstream models. This should, in theory, translate to less maintenance work by analytic engineers, less juggling multiple spinning plates, and more like tinkering with a finely tuned engine. Downside of this approach is that analytic engineers will have to be very careful adding new fields to upstream models, or else face issues such as duplicating records downstream and inaccurate aggregations at the visualization level. And sometimes this may not be immediately obvious. You may only see logic repeated in different models after some time work on the one code base. Time should be taken as a team to assess whether components within different models can be extracted and turned into their own model. And when developing new models, instead of jumping into writing all the components and CTEs from scratch from raw tables, perhaps consider if you could utilize previous models that may already be computing some steps that you might need. Words, words, words. Try to minimize the renaming of columns from source tables. At least try to keep it to a minimum, such as from the product side in the transformation layers. Renaming should occur in the final core model that you expose to stakeholders, or your choice of data tool, such as Looker or Power BI. Striving to have your columns named consistently across the transformational steps will mean an analytic engineer who needs to reference or maintain models will have an easier time joining tables and searching through the data warehouse. It may seem tempting to rename columns to something more friendly or less abstract, but this can sometimes lead to further abstraction. I'm sure many of you listening have spent ages searching for a particular field, only to later discover that it was renamed to something else. Git it, got it, good. Git and GitHub are crucial in software development, and the same applies when using dbt to build data models. Fully embrace the coding review structure involving a push to a branch and then pulling the branch into a master branch. This is a crucial step in validating models, picking up on mistakes before they reach stakeholders, and learning from one another. It provides a really great framework where more junior members of the team can learn from those more senior. This is also where you can verify whether a new model or a particular change is consistent with the coding style of the team. And a few comments on setting style guides. I know it's not the most exciting topic, but having a consistent team coding style is very important. One needs to balance individual preference with style and tools and the greater team's own preferences. These styles should not be arbitrarily chosen by management, product managers, or anyone who is not maintaining the code base. Style should be set by the analytic engineers who will be building and maintaining the transformation pipelines and core models. Whether you use capitals or lowercase in your statements, it doesn't really matter, but what matters is consistency. And if you have an automatic code formatting program, I encourage you to use them. And now I will give a quick overview of my workflow. These steps are not necessarily linear, and I often work on multiple steps at once, and sometimes return back to previous steps if something new pops up. I start with speaking with stakeholders and clarifying what data is needed. And this is where I try to understand the internal processes that generate the data and seek out the small details that may impact the model. In the planning step, I will structure how the model will work and what columns will be required and at what level of aggregation. Some filters might be necessary, and this is where I will add them. If the model is quite large, I will usually draw out the broad flows, especially if it incorporates multiple models with many interior CTEs. The exploration step involves basically searching the data warehouse for the required data. In some cases, the data may not yet be in the data warehouse, in which case I will create the necessary pipelines. This exploration step is pretty important for finding out if the data is already in an existing model. In large corporations with lots of data, many data experts can require a bit of research to look through the models and read documentation. And the last thing you want to do is build a model that already exists. Finally, I begin the model. I usually start in a SQL runner IDE, such as dbeaver, building one CTE at a time. If it's a large amount of data, I will filter the initial CTEs for one particular customer ID or vehicle ID, so that I have many events across time in which to assess the transformations I apply in each CTE, and so that the model does not take too long to return results. Once the model has progressed to a point where I'm getting through the rough output I want, I move on to VS Code, create a new branch, and add the model into an appropriate folder in our dbt repository. This is also when I will add the necessary dbt-specific code that builds the table in the data warehouse when I use dbt run. And if the amount of data is quite large in the table, I will then add the incremental logic to the model. Next, I will test to make sure that a model is created successfully in my local schema. Again, depending on whether the model has a large amount of data, I might filter for only one customer or one vehicle in the where clause. This I will remove when I finally commit the model, but for testing purposes, this is fine. Lastly, I begin the process of manually verifying the model contains the data I think it does. This is space enough for its own talk, so I won't mention too many points. I usually check basic distinct counts, verifying timestamps are correct. Monthly summations add up compared to previous models. There is an art to testing, and you really can't go overboard here. Try to cover as many bases as you can. And now, upon closing, a list of banal platitudes. You can always learn from looking at how others structure their models. I'm always looking out for a better way of expressing a model and finding a more efficient method. There is usually more than one way of building a model, and the road to a semblance of perfection is a long, arduous process. I encourage you to build sequentially, one block at a time, and don't be afraid to go back and improve the logic. Robust models are generally better than finely coded models with elaborate structures that can break easily. And lastly, be kind to yourself. Building perfect models from scratch is a folly endeavor. And that concludes my talk. Thanks everyone for listening, and I believe I haven't used up all my time, so we have a few minutes for questions.
So for example, lowercase and uppercase?
I started with uppercase because it makes it different to the rest of the code, but we use lowercase at tier, so I suppose I can say lowercase.
So as you mentioned, consistency of naming across the line is the key, but sometimes when visualizing for stakeholders, it could be more challenging to use the existing names from the backend. What could be the solution for this?
So in Looker, you can have an alias for these columns. So I would have the actual column consistent and then the alias changed to a more easier to read name for the stakeholder. So something without the underscores.
When would you advise to use intermediate models?
If you're building a large model, there might be a stage where you have to build something that requires quite an intensive amount of processing. And so you have to basically break it up. And the intermediate step is the stuff that does all the basically heavy computation. And that's not exposed to any end user apart from the analytic engineers. And that just pipes in data to the final model that you expose to Looker and the rest of your analytic ecosystem. So generally, I would say when the whole model itself is becoming too computationally expensive, you should break it up.
Since you're also using Looker, how do you decide on what to do model in dbt and what in Looker?
That's a great question. A lot of people will probably disagree with me here. I advocate for having as much computationally intensive stuff on the servers that you're paying for rather than Snowflake. The reason being that you don't necessarily know what Snowflake server's doing, and they might be hosting other companies' dashboards. And so better to do all the processing on the servers you can control and pay for. That way that little hiccups in terms of processing a model and things can be just faster. Everyone might have other thoughts.